Question 50. In the DC-DC converter shown, the switch Q is switched at a frequency of 10 kHz with a duty ratio of 0.6. All the components of the circuit are ideal, and the initial current in the inductor is 0. Energy stored in the inductor in millijoule, rounded off to 2 decimal places after the end of 10 complete switching cycles is dash. The NPTEL video reference for this particular question is Fundamentals of Power Electronics, Week 7, Lecture 8 by Professor Vivek Agarwal, Department of Electrical Engineering, IISc Bangalore. The useful data for this particular question is to know the equations, the steady-state equations of the buck-boost converter. The circuit asked in the question is a buck-boost converter. For a buck-boost converter, the ratio of output voltage to the input voltage, that is V0 to Vg, is given by d by 1 minus d, where d is the duty ratio. Similarly, the current ratio, the output current to the input current, is given by 1 minus d by d. Actually, the current ratio is obtained from the voltage ratio by making the equation or equating the input power equal to the output power. So we will get the current relation. Similarly, the current ripple that is present in the inductor is given by the formula Vg by L into dTs, where Ts is a switching period, and similarly the voltage ripple across the capacitor or across the load is given by V0 into dTs divided by Rc, where R is the load, C is the capacitance. So these are the relations that are to be understood while we are dealing with the problems related to buck-boost converter. Similarly, the other basic converters such as buck converter and boost converters, a similar set of relations are to be known. In this question, the frequency is given. The switching frequency FSW is 10 kHz. The duty ratio is given to be 0.6. The initial current in the inductor is 0. That is, the converter is starting. We have to determine what is the energy stored in the inductor at the end of 10 switching cycles or 10 TS. At the end of 10 switching cycles, what is the energy stored in the inductor? We have to determine. So, first we will understand the converter. So, between 0 less than or equal to t less than or equal to TTS, we know that the MOSFET Q is conducting. Therefore, the circuit becomes here I am taking the polarity of the inductor like this. So this will be my inductor voltage polarity. The inductor current direction I am taking this way. So in this case, we came to know that the voltage across the inductor VL of T is 50 volt. And this interval is for a duration of dTs, or which is equal to 0.6 into Ts. Similarly, during the interval in which Ts is less than T less than or equal to Ts, we will get the diode to be conducting. So in this case, the circuit becomes 50 volt, 50 volt, the voltage polarity VL of t, and the inductor current IL of t. So in this case, the inductor VL of t is minus 50 volt, and this interval is for a duration of 1 minus dts, which implies the effective duration is 0.4 into ts. So we came to know what is the voltage that is seen by the inductor during dts and 1 minus dts interval. Here I am drawing a plot of the inductor voltage as well as the inductor current. How the inductor voltage and current waveforms are there in the converter. So first is the inductor voltage, then it is the inductor current. We know that the inductor has a relation, the voltage across the inductor equal to L dIL of t by dt, or can be written as VL of t equal to L dIL of t by dt. So we know that the voltage during dts period is 50 volt, and 1 minus dts period is also 50 volt but with a negative polarity. So this is our dts period and this is our 1 minus dts period, effectively completing one switching cycle. Correspondingly, we have to determine what is the inductor current. So as per this relation, we will get the inductor current, or we can write IL of t equal to minus infinity to t, integral of minus infinity to t, VL of t by L dt. So it can be split into integral minus infinity to 0 VL of t, and take 1 by L outside, dt plus integral 0 to t 1 by L VL of t dt. So this is our initial current. I'll call this as the initial current. So that will be I naught plus 1 by L integral 0 to t VL of t dt. Here in this question, the initial current I naught is given to be 0. So this turns to be 0. So correspondingly, if we are drawing the current as per the applied voltage across the inductor during turn on, the inductor starts from 0 current. So here the inductor rises with a linear slope. The slope is given by 50 by L, and at Ts it reaches a maximum value. At dTs it sees a negative voltage of 50. So the inductor current falls with a slope of minus 50 by L. Here this duration is for 0.6 into Ts, and the falling duration is for 0.4 into Ts. That is 0.6 Ts corresponds to dTs time interval and 0.4 Ts corresponds to 1 minus dTs interval. Similarly, during the next cycle of VL, that is again the voltage will become 50 volt and correspondingly during the 1 minus dTs during the second cycle, the voltage become minus 50 volt. Correspondingly, the inductor current will again rise up to this dTs of the second cycle, and during 1 minus dTs of the second cycle, the inductor current will fall. So this process will continue till the 10th cycle. So the thing is that if dTs was 0.5 Ts, it will reach to a maximum value. 1 minus dTs will also be 0.5, so that the inductor current just touches the time axis, or the inductor current becomes 0. But here in this case, as the charging interval, that is the dTs interval, and 1 minus dTs interval are not the same, there will be an effective increase in the inductor current. So here, the effective increase in the inductor current during each cycle is given by this value. So I'll write it as the effective increase in inductor current IE. So the effective increase in inductor current IE can be written as the slope of the inductor current during dTs into 0.6 Ts. So this will correspond to the value, this value, that is the peak value, minus we have to reduce the inductor current during 1 minus dTs interval. So the inductor current at the end of 1 minus dTs or the end of Ts interval is given by 50 by L into 0.4 Ts. So this is the effective increase in current at the end of first switching cycle. So here can be written as 50 by L into Ts, we can take it as common, into 0.6 minus 0.4. So if we plug in the values, 50 by 10 into 10 power minus 3 into 1 by 10 cube, as the switching frequency is 10 kilohertz, it is nothing but 10 power 3 into 0.2. So this and this will cancel. We will get 0.1 amp. So the effective increase in inductor current IE at the end of first cycle is 0.1. Now we have to determine the increase in inductor current, the increase in IL at the end of 10 Ts. So which will be nothing but effective increase in inductor current during first interval into 10. So it will be 0.1 into 10, which will be 1 amp. So the energy stored in the inductor, the energy stored in the inductor is given by half L I squared. So the energy stored in the inductor at the end of 10 cycles, I'll call it as E10, which will be equal to half into the inductor value is 10 millihenry, 10 into 10 power minus 3 into 1 square. So it will be 5 into 10 power minus 3 joule or 5 millijoule. So the energy stored in the inductor at the end of 10th cycle will be 5 millijoule. So the answer to this question is 5 millijoule.